So hello everyone. I am Indrajyoti Gaine and presently I am pursuing my PhD at IIT Kanpur from Department of Mathematics and Statistics, and I am a PMRF fellow, and also I have cleared my CSR NET with 108 rank. Okay. In the last class we have discussed about the things like when we can subtract two sets. Like we are given with two sets. Say we have two sets A and B. Then we have discussed about all the things like A union B, A intersection B, A minus B. So all these things we have discussed in the last class. Now we were discussing about De Morgan's law. So for that we took one example. Say U be the universal set 1, 2, 3, 4, 5, 6. A be the subset 2, 3. B be the subset 3, 4, 5. Then if we can check this like A union B, this is equals to nothing but 2, 3, 4, 5. And what about A union B complement? This is equals to 1, 2, 3, 4, 5 is there. So 1 and 6. Now what about A complement? Okay, let us discuss both the things together. What about A intersection B? Highlight this thing first. Blue color or red color. We have this thing. Okay. What about A intersection B? This contains the only element 3. Okay. So what about A intersection B complement? A intersection B complement. This is equals to 1, 2, 4, 5, 6. Okay. Now what about A complement? A complement equals to, here we have 2 and 3 in the set A. So A complement will be the rest elements of U. So 1, 4, 5, 6. 1, 4, 5, 6. And what about B complement? B contains 3, 4, 5. So it will contain 1, 2, and 6. 1, 2, and 6. Okay. Okay. So check that. What about A intersection B? A complement intersection B complement. So if I check A complement intersection B complement, we will get first 1, then 6. So this is nothing but A union B whole complement. Or also check one thing, that what about A complement into union B complement? That is equals to 1, 2, 4, 5, 6. So this is nothing but A intersection B whole complement. Okay. So if I combine these two statements and just we remove this example, then what we will get? We are getting this fact. We are getting this fact. So we are getting this fact. So this is called the De Morgan's law. This called De Morgan's law. and this is called after the name of the mathematician D. Morgan. Okay, so this is these two statements called D. Morgan's law. So before we proceed further, we can check these two statements with the help of Venn diagram. So let us draw this. This is our universal set. We have defined that we represent our universal set with the square bracket, with the square or rectangle. This is our two case, and both of these two is there. So this green is our A, this is our A, and this blue is our B. Okay. So what about A complement? Okay. What about A complement? A complement means the green portion. Okay. This is our A complement. Okay. And what about B complement? B complement is this portion out of this B. Okay. Whatever outside B is considered as B complement. Okay. Then what is the common area of A complement and B complement? That is, what about A complement intersection B complement? So clearly one can observe that the common area between them are these portions, this yellow portion, right? This yellow portion. This is the common area, and we can call it this yellow portion is nothing but A complement intersection B complement. Now draw the same picture and check the other direction. This is our B, and this is our A. And what is our A union B? A union B is nothing but the inside portion, that is this portion, right? So what about the complement of A union B? Again this portion. Again the same portion we will get. Okay, so this is called A union B whole complement. Okay, and clearly we can see that these two sets are equal, and in similar way we can prove the other thing, that is whenever we have A complement union B complement, this is equals to A intersection B whole complement. Okay, so using Venn diagram we can prove these statements. So okay, so what is the statement of De Morgan's law? So De Morgan's law says, De Morgan law, De Morgan's law stating that complement of the union of two sets is intersection of their complements and complement of the intersection of two sets is union of their complements. So this is our De Morgan's law. Okay. So one thing, so some more examples. Okay. So what about A intersection A complement? Okay. So this is nothing but phi. Why? Because in Venn diagram, or else you can also understand these things now, that what about the elements of A and what about the elements of A complement, there are no common element. Why this is so? Because if we draw the Venn diagram, this is our U, and this is the set A, and A contains these elements. And what about the A complement? A complement contains these elements. So there are no common element. So A intersection A complement must be phi. Okay. Now what about A union A complement? A union A complement. This is equals to the universal set U. Now what about phi complement intersection A? So what is phi complement? Phi means null set, or the set which contains no element. So the complement must contain all elements of the universal set. So phi complement is nothing but the U intersection A. Now, as we know that A is subset of U, we can say this intersection will be equals to A. Okay, so this is the reason, as A subset of U. Similarly, what about U complement intersection A? What is U complement? U complement is phi, because U contains all the elements. So what about the complement of that set? The set which contains no element. And if we take the intersection with the other set A, then it must be phi, since phi subset of A. Okay. So these are some easy observations. These are some easy observations. Okay. So some more examples, or you can say observations, are like, okay, one, A can be, okay, first of all, A minus B, this is equals to A intersection B complement, like that. A intersection B complement. Okay. So A minus B equals to A intersection B complement. Why this is so? So in Venn, first of all, check this in Venn diagram. This is our the set, universal set U. This is the set A. This is the set B. So what about A minus B? A minus B is nothing but this set. Now, this is our A minus B. Now, what about A intersection B complement? So B complement means the other side of the set which contains no element of B. Okay, so if we take the A complement, A intersection B complement, what we will get? Let us check again. Let us draw a Venn diagram. Another U. This is our universal set. This is the set A. This is the set B. And what about the B complement? B complement is the set, this one. This is our B complement. Now we are taking intersection of B complement and A. So we get this portion. We get this portion. So observe that in both case we are getting the same set. Okay. So we can say A minus B is equals to A intersection B complement. So using Venn diagram we have proved this statement. Using Venn diagram we proved this statement. So in some cases this statement is very important because sometimes it will be easy to handle with this statement, and that's why we can use this whenever it is convenient. Okay, now check that A equals to A intersection B union A minus B. Okay, so first check with Venn diagram, then we will go with the proof. So okay, this is our set U. U is our universal set. This is our A. This is our B. So what about A minus B? A minus B is the blue portion. This is our A minus B. Okay. A minus B. And what about A intersection B? That is the white portion. This is the A intersection B. This is called A intersection B. So clearly one can check that the set A is nothing but union of A minus B and A intersection B. Right? So using Venn diagram it is clear. Now what about the proof? So write it like this: A intersection B, A intersection B union A intersection B complement. So this is nothing but A intersection B union B complement. Why? So we have already discussed the distribution law of union and intersection. So using that statement we can write this line. Now what about B union B complement? No, okay, B complement is not like that. We are denoting it by B dash B prime. You can say B prime. So what about B union B prime? So this is nothing but the universal set U. And what about A intersection union, the universal set? That will be A. Okay. So we have proved this line. A union intersection B union A minus B. This is equals to A. And also we have verified this statement using the Venn diagram. Okay. Next one is A union B minus A. What is this? This is equals to what? So first draw the Venn diagram. And this is the set A. This is the set B. What about B minus A? This is the B minus A. This is our B minus A. And what about our A? A is the blue lines. And we know that this set is A. So what about A union B minus A. So we can clearly see this set is nothing but the white portion, right? So this set will be equals to A union B, or we can write it in red. We have not verified it, so we can write it in red. This is our assumption that it can be happen, or using Venn diagram we can see that this may happen. Okay, so let us prove this. What we are getting and what we are assuming are equal or not. So what about A union B minus A? This is equals to A union B intersection A complement. This is equals to A union B intersection A union A complement. Not like complement like this. We can complement in a different manner. Applied. Okay. So we get A union B intersection the universal set U, and this thing is equals to A union B. Why? Since A union B is subset of U, the universal set. Okay. Okay. So whatever we were assuming, this is totally correct. And we also have shown that the Venn diagram, using Venn diagram, we can easily see many of the things. So it will be convenient if we use the Venn diagram to easily solve any question. So in general, it can be difficult in set theory that understanding an answer or understanding a particular concept. So it will be very much easy if you use the Venn diagram and draw the image, so that we can understand what the requirement and how we can approach the required set or required condition. Okay. Now, next statement is, what about A union B? Sorry, not like that. Intersection B. A intersection B. To just use the distribution law. So what will be the distribution law? A union A intersection A union B. Now what about A union A? This is equals to A. And what about A union B? Okay, so like that. A union B is okay. It's the same thing. It will happen, and both the things are easily can obtain. So it will be easy to use the Venn diagram. This is our set U. This is the set A, and this is the set B. What about A intersection B? This is the white portion. This is our A intersection B. And what about A union A intersection B? So we are taking union of this set A and this set A intersection B. So clearly this is equals to A, as A intersection B is a subset of A. So in the when we have when we were discussing the union and intersection, we have assumed the condition that, or not assumed, we have shown the condition that A intersection B is equals to A if B subset of A, and A union B is equals to A if B, sorry, this is the condition. A intersection B equals to A if A subset of B, and A union B equals to A if B subset of A. So this is the logic we have used here. And in a similar manner, we can show that A intersection A union B, this is equals to A, since A is subset of A union B. So just using these two logic, we have obtained these two results. So these are two important results. So we can use these results for some convenient places, so that you can easily manipulate or compute some calculation. Okay. Now give one example, like 5. Suppose we have, A intersection B is equal to A union B. For two sets A and B. Suppose we have A intersection B equals to A union B for two sets A and B. Okay, so what can I claim? So by Venn diagram, it is saying that if we draw, this is our U. So they are saying that in some case, this is our A. In both cases, this is our B. So they are saying that the A union B, like this set, is equals to this set. So they are saying these two sets are equal. So when it can happen? So to happen this, okay. So this will happen. This will happen if and only if, okay, if and only if, this will happen if and only if A equals to B. Okay. So if A equals to B, then what about A intersection B? That must be equals to A or B. And what about A union B? That is also equals to A or B. So both are same. Now what about reverse? So if I have A union B and A intersection B, then we can write it. We have A union B equals to A intersection B. So both the sets are same. Okay. So okay, what about A union B minus A intersection B? This must be 5. So we will get A union B intersection A intersection B whole complement. This will give, this is equal to 5. I don't think this will work. Okay, intersection B complement. Okay, A union B intersection B complement. This is equals to 5. Okay, this any, okay. From here we can do anything. A union B, A complement union B complement. Okay. No, I don't think it will work properly. It will be difficult to understand from here. Okay. Okay. So from Venn diagram, it is obviously clear that these two conditions will happen when if and only A equals to B. So from Venn diagram, we can say this thing. So for there, A intersection B, this is equals to A union B if and only if A equals to B. Okay. So till now, we have discussed many things about union and intersection. So now one remark, and that also using the Venn diagram. This is our U. This is the set A. This is the set B. So what about A minus B? This is our A minus, okay, not like this. This is our B minus A. This is our A minus B. And this is the set. The set A intersection B. Okay. Okay. So clearly one can check that A intersection B intersection A intersection B, this is equals to 5. That is A minus B and A intersection B are disjoint. Similarly, B minus A intersection B, this is equals to 5. And obviously A minus B intersection B minus A, this is equals to 5. That is A minus B, A intersection B, B minus A are mutually disjoint sets. So this is clearly you can see, because what about A minus B? This is the A minus B set. What about B minus A? B minus A is this set. And what is our A intersection B? This is the white portion. So clearly one can see that there are no overlapping sections between these two different sets. Section B. Now using this fact, we can prove some statements about cardinality of A union B, A intersection B, and all these things. Okay. So before that, let us suppose that if this is our Venn diagram, this is the set A, this is the set B. Okay, now we have discussed about A union B. Now one can ask, what is the cardinality of this set? So what is the cardinality of union of these two sets? Now one can easily observe from the drawing of Venn diagram that A and B both has disjoint elements. Okay, that is here A intersection B equals to 5. Yes, yes. So this thing can be easily seen. The number of elements in A union B is nothing but number of elements of A plus number of elements of B. So number of elements of A plus number of elements of B. Because in A union B, we are collecting all elements which are either in A or in B. And here A and B has no common element. So obviously the number of elements in A union B must be the number of elements of A and number of elements of B. Now what if A intersection B, this is not equals to 5. In that case, let us draw the Venn diagram again. This is the set A. This is the set B, and we have the common position, that is the A intersection B position. Okay, so what about cardinality of A union B? So this thing can be written like a different way. So cardinality of or n of A union B, this can be written as n of A minus B union A intersection B union B minus A, right? Because this is our A minus B, this is our B minus A, and the white portion is A intersection B. So A union B, the set A union B, the set A union B is nothing but a union of these three sets: A minus B, A intersection B, and B minus A. Now we have a remark that these are mutually disjoint sets. This is our remark 1, and already we have proved that if A intersection B equals to 5. Okay, so this is our remark 2. Using 1 and 2, we can clearly write the line A minus B plus A intersection B plus B minus A. Why? Because they are mutually disjoint, and for mutually disjoint sets, we have this statement. For mutually disjoint sets, we have this statement. So using that statement, we can clearly say this thing. Now, what about the cardinality of A minus B? So cardinality of A minus B is nothing but cardinality of A minus cardinality of A intersection B. Why this is so? Because A equals to A minus B union A intersection B. Already we have proved this thing. What we have proved here. Here we have proved this statement. So A equals to this. Now what about cardinality of A? This is equals to cardinality of A minus B plus cardinality of A intersection B. Why this is? Because these two sets are mutually disjoint. That is, the intersection of A minus B and A intersection B are 5. Since okay. Since A minus B intersection A intersection B is equals to 5. Now from here we can write cardinality of A minus B. This is cardinality of A minus cardinality of A intersection B. Okay, so we have used this statement here. We have used this statement here. So ultimately we have obtained the result. Okay. Similarly, we will not change anything for A intersection B. And what about this another term? This is nothing but cardinality of B minus cardinality of A intersection B. Okay, a similar statement we have used here. Now, if we box it, we can box, and if we find a result here. So from there, if we rearrange the terms, okay, let us write the term as it is. Of A intersection B plus cardinality of A intersection B plus cardinality of B minus cardinality of A intersection B. So this will cut when we will left with cardinality of B minus cardinality of A intersection B. So we have proved that A union B equals to cardinality of A plus cardinality of B minus cardinality of A intersection B. This is the formula for cardinality of, for counting the cardinality of A union B, A intersection B, and the cardinality of A and B. And using this formula, there are several questions in joint. So this is very important statement. Okay. Okay. And there is another statement which is for A union B union C. A union B union C. That is equals to cardinality of A, cardinality of B, cardinality of C minus cardinality of A intersection B minus cardinality of B intersection C minus cardinality of C intersection A plus cardinality of A intersection B intersection C. This is another statement, and we can also increase this number of sets to a finite number of terms. So we can increase this statement up to finite number of terms, and we call it inclusion-exclusion principle. We call it inclusion-exclusion principle. Okay, so we will prove this statement in the next class. And now we will see some example of the above statement. So let's start the first example. So suppose question: if X and Y are two sets such that X union Y has 50 elements, X has 28 elements, and Y has 32. Y has 32 elements. Then how many elements X intersection Y have? Okay, so before proceeding further, okay, we have discussed these things. Okay, further we don't need to discuss this thing again. So okay, so what is the question? If X and Y are two sets such that X union Y has 50 element, X has 28 element, Y has 32 element, then how many elements X intersection Y have? So let us understand the question using the Venn diagram first. a big diagram so that we can understand the proper setup. This is our U. We don't know what is our U, but yes, we have the U. So we have drawn the U. This is the set A. This is the set B, and the white portion is their intersection, and the red portion can be their union. This is the union. Okay, so we have defined four sets. Okay, so what about the red portion? So the red set contains 50 elements. X contains 28 elements. X contains 28 elements. Y contains 32 elements. So what about our this white portion contains? So obviously, check one thing that 28 A equals to 28. That means the whole portion contains 28. The whole portion contains 28. Again, B equals to 32. This means the whole portion contains 32. And so there must be some common elements in A intersection B, and they are counted twice if we add NA and NB. Okay, so we need to find that thing. So we will use the formula. We will use the above discussed formula. Cardinality of A union B. This is equals to cardinality of A plus cardinality of B minus cardinality of A intersection B. So if we just manipulate this statement again, so we will get cardinality of A plus cardinality of B minus cardinality of A union B. Yep, A union B. A union B. So what is N of A? N of A is 28 plus 32 minus 50. So what will be this? 60 minus 50. 10. So this white portion contains 10 elements. Okay, so I have discussed A and B. Okay, so it is X and Y. So we are going to replace this question by A and B. If A and B, here A union B, A, B, again intersection B. Okay, then it is clearly this fine right now. We have given the question in the XY form, and we have discussed the question in the AB form. So sorry for that, and we have now changed the statement, and now it is clear. I think A has two sets. A and B are two sets. A and B are two sets, and we have A union B 50 elements, and A has 28 elements, and B has 32 elements. Then A decision B contains the 10 elements. So thus we have found the number of elements in their common. So let us discuss a real life example. So the question is, in a class of 35 students, 24 like 24 students like playing cricket. 16 likes to play football. Now each student like to play like to play at least one of these two games. Okay, then how many students like to play? How many students like to play both? This is our question. So clearly, the number of students in the class is 35. So we can consider them as a union of these two sets. And among them, 24 students are like to play cricket and 16 like to play football. Now, one can think that this 35 is our universal set, and after that we are discussing about number of students playing cricket and number of playing students playing football. Now, yes, this is true. 35 students is the universal set, but here we have another line, that is each student like to play at least one of the two games. Okay, so this thing makes the universal set as the union of two sets. So let us denote C with the set of students, like to play cricket, and if set of students like to play football. Okay, so what is the cardinality of NC? NC is 28, right? Sorry, 24. NC is 24 and NF is 16. And for the line, each student like to play at least one of the two games, we must have cardinality of F union C equals to 35, since our universal set is nothing but F union C. So this is nothing but the N of U, and we are not bothered about that statement. So we are not writing that statement. We are writing like N equals to N of F union C equals to 35. Now use the formula. This is nothing but N of F plus N of C minus N of F intersection C. This is equals to 35, which implies N of F intersection C equals to 24 plus 16 minus 35, which is equals to 5. So the 5 students like to play answer. Okay, so thus we can handle real life problems using set theory and set theoretical notions. And to understand the problem properly, we can use the Venn diagram. And also Venn diagram is so convenient that we can easily prove many statements using the Venn diagram, as we have discussed here. The statements like this, and okay, so now we are left with the statement of exclusion principle of this statement in the cardinality of A union B union C, which is equal to this. So in the next class, we we will prove this statement first, and after that we will see few examples of both the statements, like for the formula for A union B, and the formula for A union B union C. So we will stop here today.